Based on previous class, we talking more about the interstitial diffusion and the crystal structure. Here we pick the BCC structures, and we use the equation derived from section 1 to get the diffusibility for this small solute atom located at interstitials and diffuse through interstitial size. Then you get all these results. You got the, and simply you determine there are 4 possible jumping directions, so z equals to 4. And the small r is here jump to nearest octahedral interstitial site. Then they will help you to this distance small r is a divided by 2. So here you got the you put everything here, every parameters inside each parameters. Then you finally you get the d actually equals to a square. This is a gamma prime divided by 6. So this is we call the solutions based by the equation or results you derive from section 1。就是你从公式解第一章推得的公式解，然后你可以判别就是可以跳动的方向4。然后那这个方向主要是因为我们是从octahedral 的 interstitial side， 所以你假装你自己是 solute atom 的情况之下，那跳到下一个 octahedral 的 interstitial side 的时候，那还有4个方向，然后距离是 a 除以2，然后记得是最接近的哦。这边的话就会比较远，因为这边只有2/a 嘛，但如果是这个的话，它是在后面这个面的面型，所以就会是这个 plus 这个就是 longer than this one， so this should be the shortest one。那你把它全部放进去之后，用 parameter 带进去之后，你就得到说，我的 di 事实上是 a 平方，然后这个的话其实就是 gamma prime， 对不对？然后除以6，那这个是公式解。那 so here we are going to show you the other approach. Also can get the di equals to a squared gamma prime divided by 6. And this one this method we call everything is based on fixed first law. So fixed first law, what's a fixed first law? You will probably say that the net flux equals to negative diffusivity concentration gradient. So now we're talking about the interstitial diffusion in BCC, right? So first of all, I will write down or draw the simple cubic or 1 unit of BCC structure, which are like you have 8 atoms at the corner and also 1 atoms at the center of this cubic structure. And because belongs to this interstitial diffusion, the atoms always diffuse through octahedral interstitial side. So you need to write down or draw all the octahedral interstitial side. So which means that if now you were the solute atom, you always moves through octahedral interstitial side. So here, if I use these figures and I just I just copy these figures and put here. And this is the interstitial diffusion in BCC structure. So I label all the octahedral interstitial side here and use different colors. Then I will explain why. But here, the idea by using this fixed first law would be, this is a fixed first law. So here, if I can prove that the net flux pathing, the net flux of this small solute interstitials move to right-handed side, which means that along the y-axis, if I can I can calculate the net flux for this small solute atom equals to a value which is also contain the value and also gradient term, because along y-axis, then compare these results and the fixed first law, then I will know that the di, the interstitial for this solute interstitials, equals to a squared gamma prime divided by 6. So this is how it works, right? So based on this thinking, you know that I need to get the net flux for this solute atoms. So how to get that? As you learned before, net flux, so you need to define two planes in this single cubic. So we define the alpha plane and also beta plane. Okay, because as long the net flux, how to get net flux? If I can get the net flux of the solute atom moves from alpha plane to beta plane, then minus the solute atom jump back, then you will get the total net flux of the solute atom. So this is whole story and whole ideas. So based on here, these results, we know that I need to define two planes. So here I define the alpha plane here as the center of this cubic. And on your right hand side, I define as a beta plane. And I use different x to represent all the x, no matter in orange or blue or green colors. Each x represent a octahedral interstitial site, for example, here. And on your right hand side, I got here, 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 here. So the same, right? If you compare. But I use a different color X to represent the site. For example, like at the corner, I use a blue. And on the edge, I use orange. So this is on edge, right? And on the beta, I use the green to represent all the octahedral interstitial site. This is on the edge. And here we also have a center. Okay. So now I already define the alpha plane and beta plane and also draw all the octahedral interstitial site by x. 所以我就把这个，因为我们想要用 fixed first law 嘛，所以概念上就是，如果我也可以在这个 cubic 上面得到它的 net flux， 然后我要得到 net flux， 通常就是在教你说，进的 flux， 然后我假设这个进的 flux 是往右走，因为我刚刚的 fixed first law 就是这样想，就是所以就表示说有一个 driving force 在左边很远的地方跟右边很远的地方，那有个 flux 往右走，那通过这个 unit cubic 材料还有一个 flux， 那是往右走，那是 concentration gradient。所以如果我可以把这个 alpha 到 beta 的 flux 减掉 beta 到 alpha， 也就是这个 solute atom 跳到右边的，再减掉多少个跳回左边，那就是 net flux 跳到右边的 along y 的，那我就可以比较这两个。如果我可以把它这个减完这个之后，把它写成的 form 有 contain 这个 concentration gradient 的这个 term， 我比较这两个，我就可以得到 di。那这个结果其实就是跟刚刚公式解释一样的，所以概念就是在讲。所以我的目标现在是 the first of my target, or next step will be formulate the flux of solute atom from alpha to beta plane. So first of all, you need to think about that, how to get the flux by this. So usually I would highly suggest you to starting from the unit. So what's a flux? The unit for flux is number of atoms per second per unit area. So based on the unit, is a number of atoms passing through per area and per seconds. So you can equals to gamma total jump rate times area density. So it's a number of atoms per area. So it's an area density. So flux equals to gamma total jump rate times C prime. So now I already defined two planes, right? The first one is alpha plane and the second one will be beta plane. So now try to calculate the C prime is area density. So based on your learning, you learned before, right? For the area density if the atom or the site, the interstitial site at the corner, this is we count it as a quarter, right? If on the edge is 1 divided by 2. If at the center is 1, right? So now we can roughly, based on this idea, we know that the area density for alpha plane will be, you got this is a quarter, right? So you have 1, 2, 3, 4. You got a quarter times 4. And you also have half 1, then you have 1, 2, 3, 4. Half also have 4. So for area density, you got a 1 plus 2. So you got 3. So here we have a 3, right? So we got 1 plus 2 equals 3. And 3, and this is A times A, right? This is A. A times A. So the area density is 3 atoms per divided by A squared. So this is the C prime. And next, because gamma, actually, you need to consider the possible jumping directions and also think about how many atoms, how many possible, how many, you need to consider the jumping direction and also need to determine whether each location, if the solute at each location can make a successful jump to beta plane or not. Because if it cannot, then it's not definitely contribute the flux or from alpha to beta. If yes, then you need to count it in, right? So now we need to think about here. So from alpha to beta, if you were solute atom, you locate at this orange site, you can make a successful jump, right? Sorry. You can make a successful jump to right-handed side, as I draw, right? But if you were at here, there's a host atom here, so you cannot make a successful jump to beta. The same thinking logic here. If you were at here, you were a solute atom, then you locate at here. You cannot jump here, right? So you after check for this orange site, you also can make a successful jump to beta plane at here, and the directions the same with this one, is parallel with this one, it's the same with this one, right? So all the orange, if you are the solute atom, if you locate all the orange site, can make a successful jump to beta plane by just one direction, this parallel, this just along, the direction is along y-axis. If you will locate at blue tetrahedral side, you cannot make a successful jump. So we have, so now you know that even though we have total 3 atoms, but only orange ones, which means that 2 out of 3, 二分之三只有 solute atom 只有在 orange 的地方 can make a successful jump to beta plane. So here we write down how many possible jumping directions we have. Just one. It's along y-axis. So I use the 1 times gamma prime to represent gamma. And the area density is not every atoms, just 2 out of 3 C prime. So finally we got the 2 divided by 3 gamma prime C prime. Then some people probably will question about, Professor, are you sure? Is that possible? The blue one? Yes, blue one. If you was a you locate at blue site. Yes, I cannot jump to here. But how about I jump to here? But this one is longer than this one, so usually the probability will be quite low. 如果你坐在就是你原本 在这里，那你是不能跳到贝塔。但老师为什么它不能跳到绿色的位置？因为这个绿色的距离已经高过橘色这边跳到绿色的这个 a divided by 2。This will be the shortest jumping distance。那这个比较长的，它的 probability 就会几率很低，所以 we always only consider the shortest distance jumping distance here. So this is 2 out of 3, okay? So, and the other point, that's with from here, right? So so next, this is C-prime. What is C-prime? Just remind you, it's area density. But don't forget, the fixed first law, the C here, is not the area density. It will be the volume density. So it turns out C-prime's area density, I need to try to convert it area density to concentration density. So I try to find a suitable volume for all this in tetrahedral interstitial side. Try to see whether we can convert this C prime into C volume density. So I pick up this small cubic structures, and this actually the x the distance here is a divided by 2, and within this because this cubic contain this area, and so we did not increase or decrease any the numbers of atom, and this will be the suitable volume to convert this area density to the volume density. Why? Because if I want to convert this area, I will choose the same, right? And will be choose this one, right? And this cubic is not overlap with this cubic. So it turns out this will be the suitable choice. 在我们在选择你想把面密度转成体密度的时候，原则上你选那个体积不能再让 numbers 就是原子的数目增加或减少，那要选一个最适合的尺寸，就最适合的cubic 的，就是体积的 structure。那我就会选这个，因为在这里面它不会让面密度增加，因为它多了这两个这多的这2分子 a 除以2这个厚度其实没有增加原子，也没有减少原子，只是给它一个体积。然后除此之外，我也可以观察，因为这个单位积猫都是周期性的排列，所以我也可以观察贝塔平面。贝塔平面跟这个平面其实是一样的，所以如果贝塔平面有一天要转换成体积，我也是帮它在这里再选一个。那这两个体积的 Y 轴这里都是 a 除以2，然后都没有 overlap， 所以是蛮适合的。So here I try to use I use a C prime area density divided by the distance for this cubic I specific pick for this area will be a divided by 2. So I got a C. So here I use a C times a divided by 2 to substitute C prime. So finally I got a divided by 3 gamma prime C. Then next will be quite important is because I already get the results here is a divided by 3 gamma prime C prime, right? But next will be want to know the flux for the solute atom jumps from beta to alpha. So it will be the beta jumped back to alpha. But here, if you use the same thinking logic, finally after derive here, you will get the same value with this one, because if you count the total area C prime is also half. So I got 4 halves. So also 2 atoms, and add one more at the center. So I got 2 plus 1, also 3, right? So the area density will be also 3 divided by a squared. So you got the 3 here, 3 interstitial here, okay? And the same idea, just the loop atom locate at edges that can make a successful jump to beta or alpha plane. So it turns out even I have 3 also, and this one cannot because we have a cubic, have a host atom at the center. So also 2 out of 3 can make a successful jump to alpha plane, and also just one direction. So if you try to really calculate the flux jumping from beta back to alpha, you will get the same value with this one. But it's weird, right? Because if this minus this one equals to 0, then the net flux equals to 0. So it turns out, but we know that our boundary conditions, you do have net flux passing through or along the y-axis. So you cannot use this type of expression to get the flux from beta to alpha。在这里的话，就是有同学会讲说，那我就用刚刚老师教的这个方法，就是它也是一个方向，然后它也是3颗里面有2颗可以跳过去，就在这个 edge 这2颗，因为中间这有个 BCC， 所以它跳不回去，所以就会得到一样的结果。然后老师2个相减，就2个值一样相减就是0，但我的 boundary condition 说我有一个 net flux 往右，所以这是一个不能这样表达的方法。因为这样子，你有 net flux 等于0，但你有一个你就跟 boundary condition 是不 fit， 所以它这表示不能这样解。你永远就是条件已经告诉你说，你永远都有一个 flux 往右。然后这是第一件事，然后第二件事情是，如果你也用同样的方式解的话，你就不可能有机会有一个 concentration gradient term。所以在 concentration 的 expression 上面，we have other choice。I use the other color. As we learned before, this is concentration, and this is y is a location. So I got the alpha plane and beta plane. So this will be the alpha, and this is a beta. So at alpha plane, the concentration you show is a C. You got C, right? So at beta plane, you also have a net flux move to right hand side. So I got the lower concentration at beta plane. So how to get the C at beta? Based on the mathematics, you can write down will be C plus, this is y, right? So you can have dy, the change along y, times dc over dy. So this is the expression you learn from engineer mathematics. So C plus, you can delete this C plus dc. So the change in concentration. So you also, so here, what's the dy here? Dy is the distance between alpha and beta, so will be A divided by 2. Right? Alpha and beta, so it will be A divided by 2. And this is a concentration gradient. So partial C, partial 1. So this is also C, right? So based on here, I copy A divided by 3 gamma prime, and C will be expressed in C plus dy partial C partial y. Dy equals to is the distance between alpha and beta. So it will be A divided by 2. So based on here, I successfully to create the term which we require in fixed first law. So you finally you get this minus this one. So you can, the first one is are the same. So you also only have the second term left. So you got the second term. So compare with this with fixed first law. So I can successfully to get the differentiability for this loop atom jumps through octahedral interstitial side equals to A squared gamma prime divided by 6. So this is how we use the fixed first law to solve this result to answer these questions. And some people also were, if your question asks you in terms of, like use the description say in terms of, then in terms of A and gamma prime, then you can have less results. But if they write down ask you to in terms of A and gamma, then you need to convert the gamma prime back to gamma. And here, just remember the z equals to 4. But this z, when you want to convert it back, this z is the one you learn, from here, from equation, the solution, you get the solution based on equation. The z is here, and also the r will be used this part, not the one you determine in fixed first law, this method. So the z here, and in terms of r, so a equals to 2r. It's nothing related with here. 在这里有个很重要，就是说，如果他题目是跟你说 in terms of 什么 gamma prime， 那就直接找 a 跟 gamma prime。那如果他叫你 in terms of gamma 跟 r 的话，那要记得这边的转换的 z 的判断跟 a 的判断都是用 equation 解的，那里的判断可以吗？这边就要注意。然后另外一个是说，这只是一个数学的表达方法，所以就是会有同学有点纠结这件事，所以我就想说，那我就录给大家看一下。那如果哪边有问题，就可以再问我。然后 the other very important part you need to check is you use a fixed first law， 但 fixed first law 要记得 the flux should be constant, right? So for each plan, the area density, the available area density should be identical. 所以这个话是3个，就是你用 fixed first law， 不要忘记 fixed first law 有个 criteria 是不会有新的东西跑出来，就是我是 constant 的。如果是有3颗，就一直都是3颗，每个平面都要是三颗，3个可以跳的位置。那这里就有3个，然后这里也有3个，然后因为它是重复的，所以这个也会是3个，这里会是3个位置。sorry， 这个平面，这个平面也会是3个 three in total， 3 in total and this is 3 in total， 所以看起来这个是可以用 fixed first law 的解，没有问题。这个很重要，因为在有些 case 里面，它可能每一个平面会是不一样的，那可能就不能用 fixed first law。Because when you try to use a fixed first law, you need to make sure the available total jump side will be identical for each plane. Otherwise, the net flux now equals to constant, right? But in some cases, that will be different. So first of all, I just 我在提醒你说，你在用 fixed first law 的时候，你可能要注意，因为你要用 fixed first law， 所以有些 criteria。那在这里的话，就会是每一个可以跳的平面数应该要是一样的。那有人是不一样的，你们可以做做练习。Okay, so let's do the other practice here. This one is BCC, right? So when I switch to FCC, and we have 2 different types of interstitial site, right? So if the one we assume the solute atoms always jumps through octahedral interstitial site in FCC structure. So you need to draw the FCC structures and highlight all octahedral interstitial site here. So here, actually, I already show you. You're not necessary to memory. Oh, where are they? Okay, usually I will give this type of figures to you. But here, the FCC structures, the lattice constant is A. The rate of solute atom jumping from one octahedral interstitial site to nearest octahedral interstitial site is R in specific direction. This tells you that the solute atom, if it were here, jump to the other octahedral, nearest octahedral site, the jump rates are capital R, which tell you that gamma prime equals to capital R. And the question A asks you, could you formulate the solute diffusivity, DI, in terms of A and capital R. So solute atom in terms A and capital R. So capital R is gamma prime, right? So you need to determine the Z and also the small r. So the nearest octahedral side, how many? That will be the Z, right? So half, 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 half. So all four, we have four on the upper layer level, and half, 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 half plus half. So we also have four on the same on the list level, and half, 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 half plus half, half plus half. So I have 4, 4, 4. I got 12 possible jumping directions, and the distance will be a divided by 2 square plus a divided by 2 square and square root of this value. Okay, so you got a divided by square root of 2. So I put everything back. So I got the, because this is gamma small r squared divided by 6. So I got RA squared. Okay. And the question B would be, if there's a solute concentration gradient along 1, 0, 0 is alone, there's a solute concentration gradient along 1, 0, 0, derive the solute diffusivity in 1, 0, 0 based on the net flux. So net flux tell you that you need to get the solute diffusivity DI by using the fixed first law. But usually I will double check whether the structure can use the fixed first law. So let me roughly calculate the area density for each plane, okay? So let's determine the plane here. So I just copy how to get the J. Flux is gamma times the area density. So alpha plane, so how many possible jumping, how many octahedral interstitial size? So I got the 4 at the corner, so 4 times a quarter plus 1. So I got 2 here. And here, 1, 2, 3, 4, 4. And this is A on edge. So I have a half times 4, so also 2. So here is 2. This area, 2 and 2. So each plane turns out all of them have only 2 atoms per R square, area density, identical area density. So it turns out I can use the fixed first law. So the area density, all planes are 2 divided by A squared. Okay? Then next, we need to determine the possible jumping directions and check whether each octahedral interstitial site can make a successful jump to beta plane. So let me jump to this. So here, this is, I just enlarged the crystal structure we have in prior slide. So in order to make sure this is alpha plane and beta plane, alpha and beta plane, don't forget this is extended. So this plane, alpha plane, actually can extend it to upper and bottom and front and back turn. And also the same with the beta plane, okay? So let's check whether this, if you were at the, if the solute atom at this octahedral interstitial site, how many possible jumping directions it can make, okay? So it turns out jump to beta, right? So it turns out half plus half, this one. Half plus half here. But usually this is extended plane, so I also have the other one here. And this is bottom, I also have the other one at the top. So it's 4 possible jumping directions. Z equals to 4. But this is 4, right? But I need to check whether this one is 4. That would be better if you can check each one, but I just check this one. The same idea, half, 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 and usually it's symmetry. So usually the other side, you also have the other one. So I have the half, 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 and half. So I also have 4. 1, 2, 3, 4. But this vector parallel with this one, this vector parallel with this one. So even though this can make a 4 possible jumping directions, but this 4 are identical with this 4. So only for the direction, possible jumping direction only have 4. And how about at the center, this one? Also 1, 2, 3, 4, right? Upper is half, and half. So also 4. So we have 4. We only have 4 in total. And after checking for each jumping octahedral interstitial set, all of them, 2 out of 2, can make a successful jump to beta. So this is our results. So 2, so back to here. 4 and 2 out of 2. So I got, put everything back, I got the 4R and C prime. Also the same idea. You pick up the small cubic to convert this area density into volume density. So got the AC divided by 2. So we got to ARC. And concentration here, you use the trick we just showed you. You express in 2 plus dy or dx. Here is a x, dx is partial c, partial x. So you use this to minus this one. So I only have the second term. So it will be a square r partial c concentration gradient. So I got a square capital R, the same with the solution you derive by directly using the equation. Okay, okay. So this is the other approach. So by using a fixed first law, just keep remind you that you need to first check whether whether each area density or the area density for each plane are the same. If yes, then you can use that one. Okay.